Okay. Yeah, so today we're going to define operads, which give you a nice class of monads. Okay, so a monad is this functor from some category to itself, and then there's this natural transformation from the functor composed with itself to itself that you should think of as sort of multiplication, and then there's a natural transformation from the unit to the functor, and we talked about last time we defined algebras over a monad, and we saw that for particular examples of monads you can recover lots of flavors of things that we usually call algebras, like monoids or groups or I guess because we didn't talk about how to recover what are like algebras, but okay. So these monads, these functors, parameterize algebraic structures, and we're going to talk about a sort of a special kind of monads coming from operads, and so for this class the most important example is the little cubes monad, and then we'll sort of think about like what makes this different than some of the other monads, and that will lead to the definition of operad. So that's where we're going. Okay, so we have the space C and K. It's the space of embeddings of K I-dimensional cubes into an I-dimensional cube, and then we assume that the embeddings are compositions of translations and coordinate axis scalings. And I said, like, I don't care if you want them to be squares or rectangles, it's not going to change anything. Yeah, so it's, it can be because we're assuming that these embeddings are just, translations and dilations. They're completely determined by just a picture of their image. So that's how we're going to describe cubes. Maybe rigorously their functions, but we're describing them by like pictures of their image. And if you want to topologize this with like subspace topology coming from the compact open topology on the mapping space, great. If you just like record all the sizes of the cubes and or if you just sort of record the vertices of the cubes as a subspace of like some high-dimensional Euclidean space, that will also topologize this, and it'll be the same topology. Okay. Yeah, and so we talked about given that the cubes gives us a monad. So in particular, we get a functor from spaces to spaces, which sends a space X to the space of cubes labeled in X. So rigorously, it's given by this formula. Okay, any questions? So this is a review of part of what happened last time. Okay, so I guess I should have switched X and Y here. I apologize. Yeah, so there's a definition. A symmetric sequence is a sequence of spaces, xk, with k, so k is a space with a choice of action of the symmetric group on order k. Yeah, so you should think of xk as going to be some space like this cube space. So this is a space. If you here we're saying we're fixing n and we're varying k, and this is a family of spaces, and the kth space is an action of the kth symmetric group. So here it's just permuting the order on the embeddings, or it's permuting the labels on the cubes. Okay, yeah. So this is what a symmetric sequence is. There are like, I know of like at least like 3 different names for this. Like they're sometimes called like species or FB modules or S modules or something. But Yeah, so in this class, I'm going to call them symmetric sequences, but just sort of a warning in the literature, there are lots of different names for this type of thing. Yeah, so if you have a symmetric sequence, you get a functor from topological spaces to topological spaces given by, so if you have the symmetric sequence X, so this is these spaces X to the K, you can just send Y to disjoint union of Y to the K, the kth space of X, cross over the symmetric group with Y to the K. So remember, this crossover means just the quotient by the symmetric group acting diagonally on X to the K and Y to the K. So X, the kth space of X, and Y to the K. Yeah, so given a symmetric sequence, we always get a functor, and the question is like, what structure do we need to put on X to make this a monad? A monad isn't just any functor from a category to itself. It's a functor that has it's a functor plus the data of two natural transformations that satisfy a bunch of axioms. So this is a rhetorical question. Zach or Michael can answer it, but it's not meant for. Okay. Oh, I once was like listening to some seminar talk, and someone like asked a question, and then someone raised their hand to like answer the question, and then the speaker said, "All questions are rhetorical," and then like didn't let the person answer, and then kept talking. Okay. Yeah. So what's an operad is the answer to the question. An operad is it's going to be a type of symmetric sequence with extra structure. So it's a symmetric sequence O. So that means we have these spaces OK. So with a symmetric group acts on OK. And what extra structure do we need? Well, we need basically a multiplication in a unit. So a unit here is going to be an actual element. So in the monad case, we're thinking of it as a natural transformation, but here it's just literally an element of O1. So O1 is the space in, I'm going to call OK the arity K part of the operad. That'll make sense later. So we have a distinguished element in arity 1, and then we have a choice of map from this like space in arity K across the space in arity N1 ... NK, going to the space in arity N1 plus ... plus NK. And then they need to satisfy certain unitality, associativity, and equivariance properties that I'll tell you about. And then the proposition is going to be, if you have an operad, that if X is an operad, then this functor is the monad. Okay. I guess Michael has been coerced to give a talk in this class, and he'll tell you about some sort of a way of thinking of operads as monoid objects in symmetric sequences. I couldn't find any memes about that. Apparently, computer scientists don't like operads. Okay. Yes.
Part of Michael's assignment.
What? Yeah, Michael can make the memes if he wants.
You should look at a good meme for his talk.
Yeah, or people can email Michael whatever operad memes they can find. Okay, so the most important data is this map. So let's sort of think about what is this map in the case of the little cubes. So if you specialize to, I guess, K is 3, N1 is 2, N2 is 1, N3 is 4, then we want a map from 3. We want a map like this. So, the numerology is 7 is 2 plus 1 plus 4, hopefully. I think this was wrong in my original slide. I think I thought it added up to 8 after careful proofreading. Yeah, so what do we want? We want to take this picture and like the so the output is going to be oh yeah, so maybe one thing we're going to write so this map I guess is called mu. We're going to write like O of O1 dot 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 O N K for mu of O of O1 dot dot dot. Okay. Yeah, so we're going to think of this function as like an element of the operad. An element in arity k of the operad acts on k different other elements of the operad. Okay, so now this this picture, the output of this, should be in. The output should be something in 2-dimensional cubes and 7 of them. Any guesses for what? Any guesses by people who haven't seen this before of like how to take all these pictures and produce a picture of 7 cubes in a cube? Yeah, so we want 7 cubes, and if you count 1, 2, 3, 4, 5, 6, 7 is the hint.
Well, maybe take the first one in the cube tuple and stick it inside the 1 cube, say, there. Yeah, the second one inside the 2 cube, and so on, and then forget about the intermediate cubes.
Yeah, and forget about the intermediate cubes, and then you also relabel so that like it's like 1, 2, 3, 4, 5, 6, 7. Yeah, so that's exactly it. Hopefully I have a slide. Yeah, which is hard to read, but you put this one in here, this one in here, this one in here, and then you bump up the order. So like if you can't read, this is a 4, the 1 becomes a 4, etc. Okay, yeah, so this is the this is like the structure map, the composition map for the little cubes. Oh yeah, and if you're like, oh, I don't understand what an operad is, it seems complicated, just think like, what are the things you can do with cubes? And it's like you can put cubes inside cubes. Okay. And an operad is just an abstraction of that. I believe the definition of little cubes predates the definition of operad. So it was just sort of an attempt to formalize the algebraic structure. Okay, so we have equivariance, which I spent 15 minutes making the slide, so I think I got it right. But I don't think people can process this in real time. So let's just do an example, and then we can go back to the slide later. So yeah, okay, so this is the picture from before. So the idea is that if you let's say we let 1, 3 act here. You let 1, 3 act on this cube. That's the same as letting 4, 6 act here. So there's 2 equivariance conditions, and the first is the obvious generalization of this. Yeah, so what it says is if you let a permutation act on one of the factors, then it acts on the output. That's the same as letting it act on the output, but you need to do the obvious relabeling. So here, you know, it's like 1, 2, 3, but then we're thinking of, we're thinking of this really as 4, and, you know, this really as 5. Wait, did I screw up the numbers? Oh, this is a 3. Three, 4, 5. I can't count. 5, 6, 7. Yeah, so 1, 3 acting here. Well, you just sort of use your dictionary and say 1 is really 4, and 3 is really 6. So that's like the permutation 4, 6 acting here. Any questions before I state the other equivariance condition? And if you say like, hey, I get it in this example, but like, what is the actual formula? Go pull up my slides and look at slide 9. But at least for me, the actual formula is harder to process than thinking about it in an example. Or, you know, if someone wants, I'll go back to slide 9. Okay, the other kind of equivariance is what happens if you do a permutation on the inputs. So if you swap the inputs, then is that what I want to say? Oh no, sorry. Oh yeah, if you swap the inputs, if you swap 1 and 2, that has the effect. So if you swap, you know, we'll call this cube 1. We'll call this picture cube 2. This picture cube 3. That is the same as swapping as yeah, okay, so maybe I'll call this cube C. So we're saying, okay, we're looking at C of C1 of C2, C3. If we let 1, 2 act on this C, that's the same thing as just having C act, but then you let the permutation act on the order. So if you do this swap, it's like you swapped these two labels. Ignore the output, you know, which I guess has the effect of swapping these two pictures. Yeah, so this says that basically if you let a permutation act on this outer element of the operad, it's like having a permutation act on, it's the same as having the permutation permute the order of the inputs. So yeah. Any questions? Or just sort of request for me to repeat something? Okay, great. Okay, so there's associativity, which is, again, some big formula. If you thought, like, what should associativity be, and you spent like half an hour thinking about it, this would be the only thing you could write down, but it's maybe intimidating to just read, so let's try to illustrate it in an example. So what it says is if you plug in these two cubes into this cube, and this cube into that cube, that's the same thing as, my picture right? Oh yeah. So it's like if you plug this in here, this in here, and this in here, that's the same thing as instead you plug this in here and this in there. Is there anyone who my arrows make sense to? So like the blue thing is supposed to give you that. Okay. So at least we haven't lost like the person whose research is entirely about operads. It's good. Okay. Oh, so sorry. This is not a equivariance thing. This is associativity. So what I'm saying is you can either do. So basically, you know, if you think about this, it's like we're going to put cubes into cubes, and then we're going to put cubes, then we're going to put it into cubes again. And there's sort of two yeah, okay. There's two ways of doing it. You can like first do the red operation and then plug them into the leftmost cube, or you can do the blue operation and then plug what you have left back in. So this is what associativity means. Yeah. And if you like giant formulas, go to slide 11 and yeah. Oh yeah, and there's a suggestion I should draw trees. Yeah, maybe be helpful for thinking about associativity. Yeah, so if you I'll attempt to okay. Okay, so what you should sort of imagine is this is a graph, this is a tree, and the vertices are labeled by elements of the operad. And then when you sort of contract them, you do the composition. So maybe all the vertices are labeled by cubes. Oh, maybe not this bottom vertex, but all the other ones are. Is that correct? And then it's saying you either you either sort of do this contraction or that contraction. Given that I don't have a picture for this, and seemed like a reasonable number of people are understanding, like don't worry if this tree thing doesn't make sense, but if, on the other hand, if you want me to try to make it make sense, I can talk about it more. Yeah. Okay. Yeah, that would have been helpful if I had prepped it, but since I haven't prepped it, it might be too hard to explain. Okay, and then the unitality says basically, you plug in the unit. In either way, it doesn't do anything. So if you evaluate O on k copies of the unit, you get out O again. Or if you evaluate the unit on O, you get out O. So, what should the unit be? I think I've, that's what the unit should be. In the case of cubes, it's just one big cube. So this is similar, if you think about the monad example, it was a similar picture. It's not literally the same. Before it was a natural transformation, and now it's it's an element, but yeah. the corresponding element. Okay, and then the proposition is that if O is an operad, the operad structure induces a monad structure on the associated functor. So, given any symmetric sequence, you get a functor, and then what's the extra data you need to make this functor a monad? It's like you need an operad structure on the symmetric sequence. And this is like a bookkeeping theorem, so I'm not going to say anything about the proof. Oh yeah, and we so last time we talked about the definition of algebras over a monad. I'm going to so we can just define an algebra over an operad to be an algebra over the associated monad. So like a operad will be in regular font, the monad will be in bold-faced font, and so bold O algebras we're often just going to call regular font O algebras. Okay. And there's a proposition that an O algebra is the that there's an alternate. The proposition says there's an alternate definition that just says that O algebra is can be described as the data of maps from OK cross A to the K to A, satisfying certain equivariance, unitality, and associativity conditions. So similar to the definition of an operad. And we're going to view O to the K as the space of K to 1 operations of A. So that's sort of why we're thinking of it as we use the word arity. So, CO. Maybe this would be better if this were like a comma or something. Whatever. Replace these two parentheses with a comma. So C applied to O, comma A1 through AK. So O is in OK, and A1 through AK are in A. We're just going to write this as O evaluated on A1 through AK. So we'll suppress the C, and we'll just think of it as, we're thinking of it as given, like if you fix O in OK, then you're going to get, then O is going to give you a map from AK to A. So that's why we're thinking of the operad as the space of K to 1 operations of A. And I'm not going to list these conditions, but if you think about the conditions defining an operad, you can guess them. It's also or you can just sort of think about take your operad, get a monad, think about algebras over the monad. Any questions? Okay. So the here's an example of an operad. So so it's the commutative operad. It'll be it'll just be a single point in arity K for each K. So great. So the operad is kind of boring, but maybe it'll have interesting algebras. So any guesses, preferably not from Michael or Zach, for what COM algebras are? What is the usual name for them? So there's I guess there's a guess of commutative algebra. So I guess we're in sets. So Like that would be correct if we were sort of doing the if the ambient category were like vector spaces or something, or R modules or something. I guess we're in spaces or maybe sets. So here it's sort of the analog in spaces. Yeah, so it's going to be monoids. It's going to be abelian monoids. So you can the monad associated to com is going to be n of x. So it's going to be a disjoint union. It's going to be a disjoint union of things of the form point crossover sk with x to the k. But this is, symmetric group acts on a point trivially. So this modding out by the diagonal action just mods out by the, you can forget a point and it's just a quotient by xk. So this is what we're calling sim kx. So, com of x is going to be the disjoint union over k of, of com k crossover sk with x to the k. And then, so this is just the disjoint union of sim kx, which is just, the free monoid on x. And then concretely, what are these structure maps? So point evaluated on A1 through AK. If this is part of, if A is a abelian monoid, then you just add them. So if you have an abelian monoid, the way you let point act is like this. And last time we talked about how monoids over, or algebras over this monad are monoids. Any questions on this example? Okay. The next example is the associative operad. So the arity K space of the associative operad is going to be the symmetric group on order K. And here's a formula for composition. So the permutation 1, 2, is going to act like this. So we should think is sort of like we have now I'm confused. Problem. Oh, sorry. Oh, yeah, sorry. I'm writing this. This is the permutation. 1 goes to 2, 2 goes to 1. And oh, okay. Yeah, no, this is right. Okay. So what you do is, this is saying, okay, so the output should be a permutation of the number 4. And what this is saying is that we should think of, we should sort of stack, this permutation we're thinking of as like this x. So what it says is you should take this permutation and put it on top here, and then increase the order. Sorry, I said this terribly because I myself got confused. Maybe just as a yeah. So what you so if If instead we replaced this permutation by, 1 goes to 1 and 2 goes to 2, so that would be, pictures like that, then you would keep this order, and it would be 1 goes to 2, 2 goes to 3, 3 goes to 4, 3 goes to 3. Oh, sorry, 1 goes to 2. What am I reading? 1 goes to 2. Oh, 2 goes to 1. 3 goes to 3. 4 goes to 4. So I guess with the purple, we're just taking these two permutations. I picked a bad choice. I should just pick like a 3 cycle here. So with the purple, we're grouping them like this. However, if you change the leftmost thing, we'd be grouping them instead like this. Yeah, so what you do is we have a permutation of 3 and we have a permutation of 1, and we want to get out a permutation of 4, and then this permutation tells you what order to put them in. That's probably the best way of saying this. Yeah, maybe just like, if you understand what this formula should be, maybe say so in chat, and then based on that, I'll decide if I need to say more, or if you want to ask a question or ask me to say more, just say it. So we're getting that. It is like not true that no one understands this formula, because like several people started out understanding this formula. Okay, so like some people. Okay, yes. Yeah. So I'll just say it quickly. So you you have a permutation of 3, you have a permutation of 1, you want a permutation of 4, and this outer permutation tells you what order to use. Okay. So what are associative algebras? So we need a map like this, and associative algebras are just monoids. So the way a permutation is going to act on A1 through AK is going to be you multiply them, but you use the permutation to decide what order. So, like in a, if you have a monoid and you have A and B and C, there's sort of 6 ways you can multiply them. You can multiply them like A, B, C, B, A, C, ... So, if you have a monoid, there are k factorial ways of taking k things and outputting an element in your monoid. So, the order of the symmetric group is k factorial. Great. Okay, so some informal statements. So, I guess OK is the space of k to 1 operations. You should think that operatic structures can't be used to encode inverses. So that's why we're getting monoids instead of groups. Because somehow like an inverse, I don't know, like if an inverse is like a -1 to 1 operation or something. Regardless, algebraic structures that you think of as inverses usually can't be encoded by operads. So like loop spaces have inverses at least up to homotopy, and like abelian groups have inverses. So these are encoded by monads, but they're not associated. They're not monads coming from operads. And then operads were got to capitalize. May is his last name. Peter is his middle name. I don't know what his first name is. Like John or something. Oh yeah, like if you visit UChicago, well, if you visit UChicago now, he will like not be near you presumably because he's 81 or something. But if you visit UChicago post-pandemic, he will tell you he spent like a week thinking of the name operad. And like, I think his mom was a opera singer or something. I think it's like a portmanteau of operations and monad, but like also his mom is an opera singer, is the theory. Or maybe what he tells people, I don't remember. Okay, so here's another example. So this is sort of a tautological example. So if A is a space, then the endomorphism operad of A is just the space of maps from A to the K to A. And, we'll let the unit be the unit just be the identity map from A to A. And the operad structure map is just going to be obvious composition. You write out, you have one map, and then you have a bunch of other maps, and then you can just plug in your maps into your map. And this is sort of, I haven't told you what a map of operads is, but you can guess what the correct definition is. It's a map of spaces that respects all the structure. So it turns out that a map of operads is the same thing. A map of operads from O to end A is the same data as an O algebra structure on A. So, if you're saying, oh, I don't like, if for some weird reason you don't like algebras, but you like maps of operads, then an algebra is just a map to the endomorphism operad. Okay. Oh yeah, so one thing to say, because we've been talking about operads in spaces, but they make sense, I think, basically in any category, but you don't have to work as hard if your category is a symmetric monoidal category. I'm not going to define a symmetric monoidal category, but examples include like category of R modules, or the tensor product, or chain complexes with tensor product, or sets or spaces with Cartesian product, or base spaces with smash product. Then you can define operads in all of these categories. Using the same formula, but now instead of a symmetric sequence having spaces with an action of the symmetric group, you have instead of spaces with actions of the symmetric group, you have abelian groups with actions of the symmetric group, and all of your functions, instead of being continuous functions, are maps of chain complexes, or maps of R modules, or maps of base spaces, or whatever you'd like. Okay. So with that perspective, if O is an operad, and A is an O algebra. So here, let's say, if I don't say anything, the default is in spaces. Then the homology is an operad in category of graded abelian groups, and the homology of A is an algebra over the homology of the operad. I mean, this is just sort of functoriality. You have a bunch of diagrams, you apply the homology functor, you apply Kunith, and you get, this pops out. So I guess this was kind of answered. So the homology of the homology of the associative operad, algebras over the homology of the associative operad are going to be rings. If you're someone who doesn't like spaces, you might just call this whole thing. You might just call this whole thing the associative operad. So yeah, what is this? This is like in arity K. This will be the group ring of the symmetric group, so the free abelian group on the symmetric group. Yeah. Homology of. Yeah. Oh, and this is a graded ring. This is all concentrated in degree 0 because this space is discrete, so the homology is just in degree 0. Any guesses for commutative algebras over the homology of the commutative operad? Commutative rings, I guess they'll be graded commutative. Yeah, so like degree 0, you just get commutative rings. The homology of COM is just going to be Z in each degree with a trivial symmetric group action. Yeah, but so graded commutative, whatever means some sign convention. It's the same sign convention, like the cohomology of a space isn't commutative ring, it's a graded commutative ring. Okay, so this definition is going to tell you what happens if you look at algebras over the homology of little cubes operad. So, a GN algebra, like a n Gerstenhaber algebra, if someone wants to tell me that this is an n-1 Gerstenhaber algebra, feel free to. I'm going to call it an n Gerstenhaber algebra. So it's a graded commutative ring with a product and a Lie bracket. I guess Lie should be capitalized. Only Euclid is important enough that his name isn't capitalized. And then so the Lie bracket has this degree shift. That's where the n comes in. It's a Lie bracket with this extra grading shift of n-1. And then there's a compatibility condition that involving the product and the Lie bracket. So this is what's called the in words, people describe this equation as saying the bracket is a derivation of the product. And then the proposition, which we're definitely not going to prove, but I'll sort of talk about a little bit, is the statement that an algebra over the homology of the little cubes operad is the same data as a GN algebra. So if you have a space that's an algebra over the little cubes operad, then that space comes equipped with a product and a bracket. So the product is often called the Pointryagin product, and the bracket is called the Browder operation. If you like homotopy theory, it's called the Gerstenhaber bracket if you like physics. So you have to decide which team you're on. Okay. Yeah, I guess it was first discovered or William Browder defined an operation in the homology of loop spaces, and Gerstenhaber defined an operation in the homology in Hochschild cohomology, and then I guess this is like in the 50s and 60s, and then in the 70s the operads and cubes were defined, and then it was obvious that the Browder's operation came from the little cube structure, and then it was a conjecture of Deligne that the Gerstenhaber's bracket on Hochschild cohomology came from like a little cubes action at the chain level on Hochschild cochains, and this was proven, I think, in the 90s by Jim McClure and Jeff Smith. who are who I guess were at the time both professors at Purdue. Jim is still here. I think Jeff may actually live here, but he doesn't work at Purdue anymore. Okay, so sorry for that rant. So I guess these are both 2-to-1 operations. So that this should come from the homology of the space of 2 cubes in C to the n. So what's the homology? What's the homology of the space of 2 n-dimensional cubes in a cube? Or like in terms of configuration spaces, what 2 is unrootable. 2, 1. What configuration space is this homotopy equivalent to? Other colors. So, ordered or unordered, what's the manifold at how many points? Any guesses for
it's 2 points in IN.
2 points, yeah. In IN, and then ordered or unordered?
This should be order.
Yeah, because the cubes come with an order. Yeah, so if you apply the monad, then it looks like unordered things, but we haven't applied the monad, so yeah. So then this, so we just record the center of masses and you get 2 ordered points. And then now this is equivalent to Sn minus 1. Because up to homotopy, it's just an arrow pointing from the first point to the second point. That's the data. How long the arrow is doesn't matter. And like where it is doesn't matter, it's just the direction. Yeah, so this is equivalent to Sn. So, so it has interesting, I guess I didn't write the answer, but it has homology in degree 0 and homology in degree n. So if you apply like Kunith, where does this equation come from? This equation comes from you're applying Kunith to C2, cross A, maps to A. You take homology in Kunith, you're going to get a map like this. And so, the sphere has 2 interesting homology classes. So if you plug in a generator of H0, Cn2 into here, so if you plug in bullet into here, then A would be 0, and then A plus B plus C is going to be B plus C. So this gives, the generator of H0 of the sphere gives you the product, and then the bracket, so we know that the this space is an n-1 sphere, so its top homology is Z. You plug in one of the 2 generators, not canonical, but if you pick one, this gives you a bracket. So here, this is in degree n-1, so that degree shift, A is going to be n-1 if you're thinking of the bracket. Yeah, so if you plug in a fixed class, then you just get a operation on homology of B, homology of A, tensor homology of A, the homology of A, and you plug in the bracket, then the degree shift is going to be n-1. Yeah, so whatever. That's where these 2 operations come from. It's not at all clear that this is going to be all of the operations, that this is going to generate all the operations. And it's, slightly more clear, but not obvious at all that that this is going to give a commutative ring structure. And and this is going to give a, this is going to be a Lie bracket, so it's going to satisfy Jacobi or whatever a Lie algebra is, and that it's going to be a derivation. Okay, so, this is a slide from a long time ago. Here's a list of my favorite CN algebras, and I'll just here's a picture of like what the so I'm going to plug in configurations. Unordered points in I is a CN algebra. So its homology is going to be a GN algebra, and like what is this in pictures? Well, so like this is an element. So just call this thing A. So this is an element in, I don't know, I'm thinking of this as an element in H2A. And this is an element in H1A. Yeah, so this I'm thinking of as a movie. This is a two parameter movie. It's like 2 points do a half twist, and 1 point goes around another point. And then this is, homology class in degree 1. It's 1 point goes around 2 other points. And so the output is going to be in H3, 2 plus 1 is 3. And what you do is you just put this movie on the left, this movie on the right, and you run them, independent of each other. And then the Lie bracket, it's the same thing, but now this is, so n minus 1 here is 1, because, this is like 2 plus 1 plus 2 minus 1 is 4. I'm going to go with 4. So this is in H4 of A. And what you do is you run the movie on the left, independent of the movie on the right, but then you also add, like, the picture on the right can orbit around the picture on the left. Yeah, so this is a picture of the bracket. This is a picture of the product. Any questions? And so you'll get these kinds of operations on all the other examples. So in particular, you'll get a product and a bracket on the homology of loop spaces. One sort of subtle thing is there are actually ways of constructing homology operations that don't come from the homology of the operad. So if you say, like, what are the homology operations on configuration spaces or loop spaces coming from the CN algebra structure, like, it turns out that a homology of the little cube's operad with twisted coefficients can also be used to give you homology operations. So, like, you definitely have a product and a bracket, and that's everything if you want to factor through the homology of the operad. But there's sort of more clever ways of producing homology operations, and this is what's called like Dyer-Lashev operations, which are very closely related to Steenrod operations. So homology of the operad gives you operations, but there's in fact more operations. Like the main example, and at least in this case, is if you plugged in the same picture on the left and the right, you can do a half twist instead of a full twist, and that would be a cycle. Yeah, okay, that's all I have to say today. I'm going to stop recording.